So here we go with more resistors. So if you look at how a battery plays out, and this is what we talked about. So here's this, let's say, for example, one battery goes out, hits a resistor, comes back in. Current's going to go this way from the positive around. Again, don't fight it, just accept it. So if you've got, like, let's say, for example, that's a 9-volt battery, that means if you measure the voltage across that, that's going to be 9 volts. So if you know what the current is, so let's say, for example, you know that that's 1 amp, okay? So if you go to the old standby, that V equals so then if you know your voltage is 9 volts, you divide that by 1 amp. I've got a 9 ohm resistor built into that circuit. Okay, so obviously if we measure that and that's a ½ an amp, okay, which means that there's less electrons flowing through that circuit. We take 9, divide that by 0.5, we're going to get 18 ohms. So if you're keeping the voltage the same and you observe less and less current flowing through there, that means your resistor is getting a bigger and bigger and bigger value. So let's say you get fancy and you go, well, Burkamp, if one battery is good, 2 batteries are better. Okay, so we hook up a second battery. There's a resistor, boom, here we go. So if you want to display graphically what's happening in terms of the electrons, protons, neutrons, protons, whatever particles you think are flowing through this thing. Sometimes you'll see it written like this, where you have, all right, here's our voltage, and this is like time. So let's say that you start with this little electron, and it's coming in here and it has no voltage. So what's going to happen is that that's going to get stepped up. And let's say that this is a 9-volt battery. So that first battery is going to step that thing up to 9 volts. And then you're going to have a little horizontal line. That's when it's going across that terminal. And then you would step that up again to 18 volts. And then it's going to cruise along like this, okay, when it's in that battery. And then it's going to hit that resistor, whoop. It's going to drop down, so you're going to lose all 18 volts across that. So then it's going to go along till it gets back to that battery. Then it's going to get boosted again, and so on. And so I just point this out because this is sometimes kind of a visual way of showing what a battery does, is that it takes that electron. The first battery gives it a certain boost of energy. The second battery gives it another boost of energy. It goes along. It hits a resistor, it hits a bulb, hits something like that, and then you get that drop down in energy because of that resistance. Now, let's talk about power. So, quick refresher on power, okay? Power is basically the rate at which work is done, and that's going to be joules per second, also measured in watts. So, if you look at what's on your equation sheet, the purple one, okay, so you've got PIV. P equals I delta V. So let's talk about this. So if you look at this in terms of units, so here's your current. That's joules, screwed that up. That's current, which is coulombs per second. And then you have your voltage, which is joules per coulomb. Well, isn't that clever? Okay. The coulombs cancel out. You're left with joules per second. Voila, you have power. So if you think this through, this is going to make sense. So if you go back to this analogy, so if you remove the batteries and you have no delta V, guess what? You're not going to have any power. If you break the circuit where you don't have a current, guess what? You're not going to have any power. So those two working together is what's going to get you this power calculation. So clearly, the more current that you have, the bigger the voltage that you're going to have, the more power that you're going to have available to you to do work. Now, this is where the magic happens. So there's a couple of ways you could look at this power. We're going to combine a couple of things. So we said power equals your current times your voltage, but we also said that V equals which is current times your resistance. So what we can do is we can take this idea that this is equal to voltage, and we're going to drop that right in there. I'm going to go, oh, okay, that's kind of cool. So then I can write this as power times IR, which is I squared R. Okay. So if you write it like this, then typically the advantage of doing this is that typically your resistance for a particular substance isn't going to change as long as your temperature remains somewhat constant. So if your resistor is going to remain constant, then because of the fact that this is squared, that means that any change in your current is going to have a quadratic or an exponential impact on your power calculation. So if you're using this and you double that current, well, that's going to increase your power by a factor of 4. If you triple it, it's going to go up by a factor of 3. So this is how this plays out with bulbs. So if you look at the brightness of a bulb, which like your typical bulb in your house might be like 75 watts. Oh, okay. So if you look at that 75 watt bulb, well, obviously the more power that you have here, in terms of your resistance is going to be a fixed value. So that means that your current then is going to what's going to drive that power consumption. Well, if you step that down to like a 50 watt bulb, you don't need as much power. You're not going to draw as much current. You're not going to buy as much electricity from Evergy or the energy that you're going to get off of a solar panel, whatever that's going to be. So then, there you go. All right, which is, I just realized, just one big blur right now. Now, the other way that you can look at this in terms of PIV, and we're going to go back to V equals IR, and we're going to solve this for I, and we're going to get V over R. So now if I come in here and go, okay, hey, that's going to be V over R times V, and doing some modern algebra, actually this is old algebra, not even modern, we get V squared over R. So that's going to equal that power. So if you look at it in terms of this is if you know your voltage, like let's say for example, your typical voltage in your house is 120 volts. So if you know that you've got a 120 volt system, and you know your resistance, then that's going to dictate that power. Now, when you look at this in terms of a light bulb, and this is where this gets a little bit, light bulbs are always a little bit weird. So obviously, if you increase your resistance, you're going to be dividing by a bigger and bigger and bigger number of R. As long as your voltage, and this is what you have to focus on, if your voltage remains constant, if you have a brighter or more and more and more resistance, that's going to drop that power, that's going to drop that resistance. So this is where this plays out in terms of that equation where you have resistance equals rho L A. So if you look at what's going to happen, like let's say, for example, you reduce your cross-sectional area. So let's say you take this wire and you draw it out so that it's even, so you have a smaller cross-sectional area. Well, if you have a smaller cross-sectional area, that's going to increase that resistance. If you increase that resistance, you're going to be dividing by a bigger and bigger number, and that's going to decrease your power. That's going to decrease the brightness of the bulb. So when you look at this, and I'm going to summarize all of this. So we've got 3 ways to look at power. You've got PIV, you've got I squared R, and you've got V squared over R. So you have to be able to work with all three of these equations individually, okay? This is what's on your sheet, but you also have to be able to make this substitution to get I squared R and V squared over R. Because depending upon what you're given, that's going to drive which of these equations that you're going to use. The other thing that you have to focus on is what are you going to hold constant? So typically, your voltage might remain constant if you're like hooking something up into your house. Your resistance might stay constant as long as nothing else is changing, okay? Your current and your voltage, that might be given to you, how much power is going to be dissipated. So if you look at this in terms of a problem, let's say that you've got a typical 75 watt bulb, okay? And that is in your house, and your house is wired like every other house, and that's 120 volts, so that's going to be your voltage. And you want to figure out how much power is going to be consumed. So let's go through a couple of things. So one thing, we can figure out the current. So if you start with the idea that you have PIV, okay, so your current is going to be power divided by your voltage. So that's going to be 75 watts divided by 120 volts. And that gets me 0.63, oh, that was wrong. 0.63 amps, not ohms, okay? So that tells me how much current is flowing through that bulb. Now, if we want to figure out the power, which we know, and hold on. Oh, now I know what's going with that. So now if you want to figure out the resistance of this, then you go, okay, well, then I can go Ver, right? So then I can go, okay, one option is that I know that's 120 volts, and I divide that by 0.63 amps. And let me do a little bit of math here. And 120 divided by 0.63, I get about 190 ohm resistance. So that's where I'm going to go with that. So the other thing that you can do with this is that because that's a 75 watt bulb, well, that's joules per second. So if you know how long this thing is going to run, okay, like let's say 60 seconds. So if you look at this in terms of, oh, if I take joules per second and multiply that by time, then I get units of joules. So if you know how long that bulb is going to run, then you can figure out exactly how much time or how much energy that's going to consume. Okay, now let's do a little bit of more magic with this deal. So the other way to look at power, and this is a broader idea, is that it's work done divided by time, which can also be expressed as change in energy per unit of time. And this energy could be anything. It could be kinetic energy, it could be rotational energy, it could be translational energy, it could be the energy stored in a spring, whatever this is. So the other way that you can look at it is that it's change in UI per unit of time. Now, we're going to do a little bit more substitution into here. So that's the beauty of knowing a whole bunch of equations, is that now you can start to substitute in. So now we can look at power as going, okay, well, that's Q times my voltage, which is my UI. Okay, so if you look at UI, that's all that is divided QV divided by time. So then, or QV, and then I'm going to divide that by time. Well, Q divided by time is coulombs per second, okay, which is just times voltage. Well, coulombs per second is nothing but current. And then current times voltage gets you power. So if you look at this in terms of energy, then that becomes very simple to look at in terms of, oh, okay, right? Well, this is how I'm going to calculate that potential energy, is that it's my charge times my voltage. I substitute that in there for OUI. That simplifies into coulombs per second times voltage. Boom, here you go. That's the basis of your power calculations. Okay, so let's say that I want to give you some choices here. Let's play along here. So let's say that I'm going to give you a couple of different resistors here. Okay, and here's resistor A, and it has a drop in voltage, and it has a resistance of R. And then resistor B has a drop in voltage of 2 delta V. Oh, I screwed that up. And a resistance of R. And then I've got C, which is a delta V, but it has a value of 2R for my resistance, so that's C. And then I've got D, which is a drop in voltage, and it has, hold on. Hold on, I can't read my I can't read my own handwriting here. Oh, half resistance, 1/2 R. I was confused where I'd put the two. That's what you get for not being able to read your handwriting. My God, I feel like Peyton Hoffman at the moment. Okay, so what I want to do is I want to rank these in order of increasing power. So what we're going to look at is that power in this situation, why do I keep putting an R, is going to equal V squared over R. So now if you look at it from that way, and I want to rank this in order of increasing power. So if you look at A, oh, okay, well, that's just going to be V squared over R. That's all this is going to be. Now, when you get to B, because you've got 2V, or not 2V, in this case it is 2V, and that's going to get squared, so we're going to have 4V squared over R, because that's going to get squared. And then this is going to be V squared over 2R, which is going to be 1/2 V squared over R. And then this is going to be V squared over 1/2 R. So that 2 is going to flip up here. And then we're going to get 2V squared over R. So we've got V squared over R, 2V squared over R, 1/2 V squared R, and V squared over R. So in terms of power, B is going to be the greatest dissipator of that power because of the fact that it's going to have the greatest voltage and a resistance of R. Then if you go through, then it's like, oh, okay, B is going to be, because we're going to have half the resistance, that's going to increase that power. Now, this becomes a little bit counterintuitive because of the fact that a lot of, you would think, well, maybe with half the resistance, then we wouldn't necessarily dissipate as much power. What happens here in terms of this resistor is because of the fact that, yes, it has half the resistance, but because of the fact that I'm going to have that same voltage drop, like comparing these two values over here. So this is V squared over R, this is 1/2. So this will actually dissipate twice the power, which seems somewhat counterintuitive. You'd think, well, if it doesn't have as much resistance, then it maybe shouldn't dissipate that much power. But because of the fact that it's got that same voltage drop, that's going to be the whole key to this, and because that voltage is squared. So you also have to look at what's going to happen in terms of VER, okay, and then how that's going to play out with PIV as well. So this is why when you're given in this situation where you're looking at voltage and resistance, you want to use that V squared over R equation. All right, now let's just say on one of your assignments, you're going to have to go old school, okay? And I mean old school, right? So you're going to have to warm up a substance. I think it's like a block of ice or something like that. From 20 degrees to 80 degrees, let's just say. So when you're warming something up, there's two ways that you can calculate Q. You can have Q equals M delta T C sub P, and then that's if you're warming up or cooling something down. If you're melting something, remember you've got to use like that latent heat of fusion, and you're going to use M times, I screwed that up, times the latent heat of fusion. If you're melting something, then you're going to have mass times latent heat of fusion. If you're boiling something, you would have mass times your latent heat of vaporization. So one of the problems you've got to, like, I think, melt a chunk of ice, and because I'm giving you that assignment, that scanned answer key, you can look up the numbers there. So this is kind of an old school kind of way to do this. So in terms of, one of the things it's going to ask you is how much time it's going to take. Well, remember, power is energy divided by time. So if you solve for time, that's going to be energy divided by power. So go to YouTube. You'll see a dramatic example of this with a hot dog. And like I said, you'll see this on the video. I don't recommend that you do this at home. So a couple of housekeeping items. And I think because this thing, I don't want to rush you guys, and next week is going to be fairly laid back. I'm going to send that quiz out. I said I was going to have the quiz on Friday on the calendar. I'm actually going to, I'll probably post that quiz probably Saturday, and I'm just going to need that back by Sunday. We'll talk about that in the conference tomorrow. When you guys start to send stuff in using that cam scanner app, make sure that when you change the name of that file, and just don't send it to me as like a PDF in a random generated file. Write neatly, but then on that, you want to name that thing. So like, let's say, for example, you're going to call it like Peyton, and then what it is, like that quiz. Mainly because all I'm getting in is PDF files, and if all I see are just like random numbers, then it's really tough for me to keep track of whose is who. So when you take pictures and send me something with that cam scanner app, please, I beg of you, name that file. At least put your name on it so that I can see what that is. So tomorrow we'll wrap stuff up in the lecture, and like I said, I'm just going to dump that. I'm going to put that quiz out probably Saturday. I just need that back by Monday, and we'll talk about that. So anyway, there you go, kids, and look for the YouTube video.